afternoon, and it's very delighted to see such a packed room from students, faculty, and guests from across the departments at UW. So today we have a very special seminar, which is part of the annual student invited seminar series in the Department of Biostatistics, where students every year nominate and elect a speaker they're most eager to learn from. And this year, we're truly honored to welcome Dr. Emmanuel Candes, who frankly needs no introduction from me. So Dr. Candes is the Barnum Sinus Professor of Mathematics and Statistics and Professor of Electrical Engineering at Stanford University. He is internationally celebrated for his pioneering contributions to statistical inference, high-dimensional data analysis, and machine learning. Over the years, his work has been recognized with many of the most prestigious honors in our field, including the Alan T. Waterman Award from the NSF, the George Hoyle Prize, the MacArthur Fellowship, often referred as the Genius Award, and also the Princess of Asturias Award for technical and scientific research. He's also a member of both the National Academy of Sciences and also American Academy of Art and Sciences. The title of his talk today is Statistical Inference in the Age of AI. So without further ado, please join me for welcoming Dr. Emmanuel Candes.
Well, first of all, thank you so much for this generous introduction. It's always a pleasure for me to come to UW. It's a place in the world that I really like. And this time is really special because I was invited by the students, as you said. And boy, yeah, your students are really smart. So it's been fantastic. It's been a great day so far. I hope I'm not going to destroy it in the next hour. We're going to talk about statistical inference in the age of AI. I don't know what the audience is, but it's a very statistical talk, and I hope that's okay. And so we're going to talk about AI and statistical inference. Okay, so now there's this Zoom stuff, and I have to, okay. Before I get started, maybe that's my most important slide, because everything you're going to see is pretty much done in collaboration with a wonderful postdoc, Ken Azurnich from Stanford. And if anything from this talk, I'm kind of the messenger and she's the ruler. So I think I'm going to talk about a field that I'm not saying she's single-handedly created, but not too far from it. And so it's been a privilege to work with Tiana over the years. And now I'm still stuck. Okay. So I just want to start with an example. I want to start with a scientific question. I know I'm in a Biostat seminar. I should perhaps start with a biological a health population question, but I'm going to start with a question that kind of motivated this work, which is, suppose I want to know what is the rate of deforestation in the Amazon. And so the way you usually do things is, in fact, the Brazilian government, we work on data from the Brazilian government, is, well, you send trucks into the Amazon and you measure them. And so, this involves a lot of remote sensing where you're going to send trucks, and they do this, and they go about places in the Amazon, and they measure very carefully the deforestation rate in various places. Of course, as you can imagine, this is a very, very expensive measurement process. And so the question is it possible to use other sources of information, perhaps biologics, along with machine learning algorithms to actually get sharper answers and get the kind of accuracy we need at a lesser cost than what it would take to actually send all these trucks through the Amazon. And so that's what we're going to be talking about. Okay, and so you have to help me with this thing because I have this great gift. And okay, do I need to do it like this? Not sure why. Screen keeps interrupting it. It's working now. Yeah. Okay. Well, maybe it's not going to work. No, now it's not working anymore. Okay. It's a waiting room. Okay. So I don't know. Well, I'm going to try to find one. So the problem that we're looking at here, which is a problem that's going to motivate us for all this lecture, is we have a bunch of grand measurements, but they're very sparse and they're very few. At the same time, we may have a lot of features. In this example of the rate of deforestation in the Amazon, the features might be just satellite images. And can we perhaps take off so that you can see my images?
Yeah, I was going to try to do this but I was a little afraid that I might lift the screen. Let's try it. Let's see if there's a better lighting feed.
So you see satellite images. And
There.
so so that's perfect. Yeah, so
Okay.
that's excellent. So we see some satellite images. And for each satellite images, some satellite images, very few actually, I have a ground truth label, which is the rate of deforestation, because this is a portion of the Amazon where I send the trucks. And then for a lot of satellite images, I do not have the ground truth label. So if I think a little bit about the data frame, here's what we have. We have a bunch of features. Here they are images. Very few labels because they're very costly to acquire, and a lot of images without missing label. Now, the deforestation rate would be if I could actually complete this table and observe the entire Y, then I'd be interested in for example, the mean of what the proportion of the Amazon forest that has been deforested. But I don't have that. And so I want to learn the mean of Y. I have very few samples, and we're going to discuss methods that will do better than if I'm just using the gold standard method, which is average what you have. So, okay, all right. So we have little n expert labels, and now I can use a machine learning algorithm. So this is represented by this thing, is maybe I have a ResNet, I have fine-tuned ResNet, a powerful computer vision model, to actually infer deforestation rate from satellite images. And if I had such an AI model that can produce imperfect estimates of deforestation label, it would be extremely tempting to actually impute the Y column with a prediction from my machine learning system, from this computer vision system. And so the question is, of course, my imputation model might be biased, might be completely wrong, and so I might actually not be able to infer the mean properly. The goal now is, I have a probability distribution on X and Y. There's a parameter about this distribution that I need to know. For example, this can be the mean of Y. It can also be, we'll see many examples where it might be a regression coefficient. And I want to be able to leverage the fact that I have a lot of unlabeled data to do better than what I would do if I were to ignore the fact that I have a lot of unlabeled data. Okay. And I'm sorry, but this keeps on. So for example, I might ask, what is the mean deforestation? So classically, we're going to look at the trucks we send in the Amazon. We're going to take the sample. It's unbiased. It has a variance. I mean, you all know about that. Now, there's a proposal that has a name of prediction-powered inference. It was proposed by Tiana, which we just talked about, and the group of Mike Jordan at UC Berkeley in 2023. And what they propose is a different estimate. Of course, it's very similar to things you have seen, and I'll try to make some connections. But the prediction-powered inference is essentially what we're going to do is we're going to take the prediction of the machine learning model on this entire data set. So it's across one of the entire Amazon forest. And then we know that this can be biased. And so we're going to debias it. And the way we're going to debias this is we're going to subtract to this very naive imputation a term, which is essentially the mismatch between the prediction of the machine learning model at a location for which I have a sample minus the ground truth. And so it's not going to take you very long to realize that if I take this estimate, it is also unbiased because the average of this term is exactly the same as the average of this term. And so what left is the average of the mean of the Y, which is unbiased for the mean. It is unbiased, but the enormous advantage of this estimator is that it might be more precise. Because if you allow me to simplify for a second, then if I think that I have a lot of unlabeled data, capital N is much larger than the little labeled data, little n that I have, then you can see that essentially this term goes away because capital N is large. What I'm left with is the variance of this term, and if f has some predictive power, this is much less than the variance of. And so I can win. And so when the predictions are good, I have an unbiased estimate, which has much lower variance. Now, because this is still a random sum of independent terms, the theory is actually completely straightforward. What makes classical inference work will make this estimate works. And so I can derive confidence interval, etc. But because I have reduced variance, this interval will typically be much smaller. Okay, so this is an example, and this is to show that you can do a lot of cool stuff with that. And I know that a lot of people in causal inference, I know there's a lot of expertise in causal inference in this room, will say, well, this is something we've kind of been doing for a long time. Yes and no, because, now the thing is we're going to bring to bear a lot of machine learning tools. And so now we're going to make predictions using AlphaFold with ChatGPT, GPT-4o. We're going to fine-tune GPT and so on. And so this is where the world in which this paper by Mike and Tiana and their colleagues is taking us. So here Xi is a protein sequence. Yi is an indication of a disorder. T is a relationship between a disorder and a phosphorylation. Like what it is exactly, we don't really need to know. What I want to show you is the confidence interval that these methods, three methods produce. One is a naive estimate, which is just using AI. So you're just imputing with AI, and you take the average of the real data and of the imputed data, and you get something which is biased. So it's not what you want. It has very low variance, but it's not what you want. It's not centered at the right thing because AlphaFold is biased in this example. Right? The AI prediction system is AlphaFold. In blue, you see your classical Stanford teaching stat2. And in green, you see this prediction-powered method, which is centered at the right place, but has reduced variance. And it has reduced variance because AlphaFold has explanatory power. And so what we can see is we can think about the sort of, what would it take? We could talk about the effective sample size. What would it take for the classical method to achieve the accuracy of the prediction-powered inference? This is what I'm going to call the effective sample size. So, the baseline is a naive thing, the thing that we all do. The blue line is the effective, the green line is the effective sample size that the method would achieve. And so we can see that, when n is, 800, then you have an effectively sample size of 1800. So it's like if you have 2.2 times more data. Okay. All right. And do I need to click? Okay. So I said, this is not all new. And, I don't know. I'm on record. I don't know what I can say and what I cannot say. But yes, it is not new. I agree. There's people in imputation statistics have actually worked on this for a long time, and I think we're all familiar with these techniques. I think what's new is to recognize their importance and to apply them to things that were unthinkable before. Okay, so I just want to make the connection with what people have done doing in imputation to actually show you how similar it is to a lot of things that that you probably know about. Okay, so it is very similar to what people call augmented inverse propensity weighting. So in this setting, we have n individuals with observed covariance x1, xn, and then we're going to treat individual I with probably pi of xi. So ti is equal to 1 if you're treated. And then there's this kind of famous quantity that people care about, which is the average treatment effect, which is a difference in the response to the treatment versus not. And so what people do is they can say, well, given some covariance, I might be interested in estimating the conditional treatment effect, given that x is equal to x, and the conditional mean when I get treatment versus when I do not get it. And then, people will actually try to find an estimate of the average treatment effect by essentially comparing this regression function and reweighting them appropriately. And this is called the augmented inverse propensity weighting estimate, and it has this form. And so I'm not going to ask you to stare too much at this formula. I'm just saying that this is something that people do. And when I compare this formula with what we've seen something, of course, extremely similar. We see some predictions minus what looks like to be a debiasing term, and it's absolutely correct. So it has the same form. And so if I focus on the case where pi of x is little n over capital N for all x, then, this is my estimate of the response to the treatment. All right. And then if I compare this with the proposal of Tiana and company, the prediction powered inference, this is what they propose. And you can obviously see that there is very strong similarity. I think, again, I don't know exactly how we judge the importance of an idea, but to me, it's kind of phenomenal that all of a sudden, these ideas are going to be applied to satellite imagery and lots of things of this nature. Okay. All right. So here's something a bit newer, which is, my previous slide relied on me giving you a model that can make good predictions. And think about my deforestation rate. Like, where does this model come from? Well, we have powerful foundation model, but they are now trained to actually recognize deforestation. I'm going to have to need to fine-tune them to recognize deforestation. So I'm going to have to use a bit of the data I have. So I think the people who actually wrote PPI were a bit cheating, which says when they show you performance, they conveniently train a model, pretend I did not give them data to train the model and then show an improvement, which is questionable. But in fact, they actually trained their model or fine-tuned their model on data, and then they pretended that I never gave them this data. So I think that's a bit of a problem. And so now we want to go beyond pre-trained model, which is most of the times this is what we're going to have to deal with. Usually, I may have a very good foundation model, computer vision model, or AlphaFold also has been trained, has been fine-tuned to actually recognize this relationship that I mentioned before. Now I cannot assume that I have an accurate pre-trained model. At least, at the very least, I'm going to need to fine-tune, and so data splitting would be wasteful, right? Because that's what they do in PPIs. They do data splitting, and then they pretend that they did not get the first split. So we could train and fine-tune F and apply PPI. And so we're going to try to kind of push the PPI theory, which is we're going to have a cross-validated version of PPI that works like this. So you give me labeled data, and what I'm going to do is I'm going to essentially split it into K-fold. Let's say K is 10, so I have 10 folds. So these are labeled data I have. I'm going to train a model on all the folds but the first one. So this is what I'm fine-tuning the AI model you gave me to recognize deforestation. And I'm going to pretend that this is fixed. And I'm going to compute a first estimate, which is the estimator we've seen before, but now assuming that F hat is fixed, it's F1. So it's from the point of view of I1, I'm going to compute the same estimate using the model trained on all the fold except fold 1. And then I'm sure you can see what's coming. I'm going to repeat the process. I'm going to train on all the folds but 2. And I'm going to compute the second estimate, pretending that this is my full data set. All right. And so what I'm going to do now is I'm going to calculate a new estimate, which is an average of these 10 estimates, if I have 10 folds, which is essentially the average of the PPI estimates over folds. Now, so this looks a bit more complicated, but I mean, conceptually, it's very easy. So I'm going to average out the PPI over the K-fold. So now the data appears both in training, fine-tuning the model, and to debug. So now the same data point here is going to be used sometimes to debias when I'm training on the other fold, and all the other time to actually train the model. So it's not wasteful. And now the form of this estimate is basically the average of the prediction if you were to trust your AI models, and then you correct them by the debiasing term. Now, of course, the theory is going to be more hairy because now there's not a sum of independent random variables anymore. You have to be careful about how you do stuff, but this is a cross PPI strategy. Okay, now each time someone is doing something on Zoom, we have a problem. Okay, so everything, the cross PPI, even for the PPI theory, was easy because you have a sum of independent variables. You have the variables are coupled, and so that's a problem. But you know, the CLT does not apply. But nevertheless, I'm going to skip the theory. I'm going to say that at the end of the day, you can estimate by bootstrap methods the standard deviation of your estimate. And then, you know, things are reasonably normal. And so you know how to construct a confidence interval. All right, so the theory goes through, and it takes some pain, but it goes through. And what we can see is that, you know, it's exactly now it's my deforestation example. We've seen AlphaFold. Now we're going to see ResNet fine-tuned to actually find regions of high deforestations. And so you see that all these methods, so we have this cross PPI which I've just talked about. We have the classical version. So the blue curve shows you the coverage as a function of the sample size. And so statistical theory works. You want 90%, you get 90%. All methods achieve the coverage, but among those, then the PPI, which seems to be sample efficient, has shorter intervals. So it has lower variance. And I think another thing I wanted to show you is that two things happen. Is that when I use PPI, so you know, if I were to do sample splitting to estimate the model at first split and then bias on the other one, you're going to get a lot of variability because you know one thing we don't talk a little bit about when we do sample splitting is that there is a randomness due to the sample split, which you can see here. So not only is the blue bar are larger than the orange bar, the cross PPI, but they're also quite moving around because they very much depend on the sample split we took. And so it's over repeats of the sample splits. This is a cross PPI estimate. They're shorter, but they're also far more stable. This procedure is not completely randomized, but it's not crazy. And of course, it will be less and less random as you make more and more folds. Yes?
Question. So here, the classical has narrower width than PPI.
Yeah, and it's because sample splitting is not effective. So you use a lot of too many samples to actually, and you could not recuperate this half sample that you lost to.
So this is PPI with samples.
Right. It's PPI with. I don't know how to do PPI otherwise. Nobody has given me a model that actually recognized deforestation in Amazon before I looked at the imagery, and before I actually used my labels. Okay. All right, so I'm going to have to go back to the podium always. Okay. So I just want to, I talk about the mean, but you could do anything with this. You know, anything that falls into M estimation. So you could have any parameter theta that is a solution to minimization problem over the population of your joint distribution of random variable x, y. This can be a regression coefficient and so on. So of course, this could be regression coefficients. This can be a lot of different things. And so what you ask is not what does the estimator look like when we are trying estimating things that are not means, but what an M estimator is about, the minimizer of this population loss. Well, it's exactly the same thing as before. We're going to impute using our machine learning model on all the folds but the J's. We're going to basically average the losses of the imputation of the AI model, and then we're going to debias it. So we're going to play the same trick as we did for the mean, except we're going to do it in loss rates, right? So this would be essentially the naive loss. This is just using AI only, and we know that it's not quite right. And so we're just debiasing it. And so we're doing exactly what we've seen before, which is we're using our imputation, and then we debias a loss function using the real data, right? And so this is my debiasing term. Now, you might be worried about this. I don't know if you're worried about this. You know, so I don't know, like just I'm going to throw out there a word you might have, which is that this loss function is convex in theta. So we know how to minimize this because convex analysis. The problem is here I have a convex function that subtracted you might lose convexity. So actually finding the minimizer of these things might be a problem. There's some nice models in which this is not a problem. So you might not have convexity because this term is convex, but then it's convex plus concave. I mean, we now have a lot of excellent algorithms for minimizing some of the convex plus concave function. You just draw the tangent, you solve, and you redraw the tangent, and so on. I just want to say that if this is a log likelihood associated with all the models you know about, the good thing is that the non-convexity goes away and you're back with the convex problem. So when you do linear regression, logistic regression, GLMs of all kinds, if that's the inference you're looking for over this parameter, then basically the good thing is the partition function is the same. And so that's the thing that causes loss of convexity. But because you add the partition function and subtract it, you're left with a fine term, and we are good. In other words, this term goes away. And so that's good. So we know how to do these things in practice. And, you know, we can do linear regression, and maybe I'll skip this, but you can do pretty much anything you like. Okay, and so same thing. It's possible to derive formulas or estimate formulas using bootstrap style method. And at the end of the day, we're going to have confidence interval that has a prescribed coverage. Okay, so it's we can do means, we can do quantiles because they're minimizers of pinball loss, we can regression coefficients, we can do a lot of it. All right. Okay, so this is census analysis. So we have a bunch of, I'm showing this example because that's an example of inference about a regression coefficient. And then it's going to show the same problem as what we've seen with PPI. So X are demographic covariates, Y is income. And I'm interested in understanding the effect of age and the Euler's coefficient between age and income. All right, and now my F, the prediction model that I'm going to use to actually infer Y is not at all a linear model. It's like XGBoost. All right, and so what we see is the kind of plots we've seen before where all methods achieve coverage, and yet the PPI suffers because it suffers from this sample splitting, and then the cross PPI is maybe what you might want to use in a situation like this one. So we can do means, we can do regression coefficients. We'll see that we can do other things later on. Okay, and so now there are practical considerations which people must be careful about. We've seen worrisome examples where PPI is not as good as the naive method. And so this has led a field called power tuning. And so one thing you can do is you can introduce a parameter lambda that basically controls the size of the debiasing term. And so, so this is exactly the formula we had before. And now what we're going to do is we're going to have a debiasing term. So the term that is multiplied by lambda is actually going to be a term that, you know, makes sure that this is unbiased for the loss. But the thing is, before we chose lambda to be equal to 1, it doesn't have to be 1. It can be anything you like, such that the variance of this estimate is minimized. So perhaps we don't want to parse as this complicated formula. What I'm trying to say is if this were the mean, so this is the squared loss, then the minimizer of this thing will just be a convex combination of the classical estimate, which uses only actually labeled data only, and the estimate we've seen before, let's say the cross PPI estimate. And you have to write the choice to choose lambda to achieve minimum variance. So when lambda is 0, you have classical inference. You just don't look at the unlabeled data. When lambda equals 1, you do what you've seen, but perhaps a better solution is in between, which is a topic that we're going to revisit later on. So what what people recommend you do in practice is that you tune lambda optimally so that you have two extreme points. You trust the PPI view of the world enormously, or you just don't trust anything and you go somewhere in between to minimize the opposite. This is called power tuning, and we're going to come back to this picture in a second. Now, one thing I realize I'm a bit scared about is that it's possible that there are people in this room who know more about this topic than me. I met some of your students, and they're already exploring this with the debiasing term is not even the loss, it's something else. So I'll talk about this in a few minutes. Oh, well, speaking about this, I want to mention the work of a student at Stanford, Wen Longji, Li Wale, a former postdoc, and Tiana, a current postdoc. They work together to show like if you actually believe this state of the world, and I think Dwight and Daniela here are working on things that are very similar, I learned today. You might want to minimize your loss function. So this is using data. And so now we're going to use the imputation of this model to add a term. So you can look at the PPI estimate as let's minimize a loss over label data plus something. And before we use the loss function here, but there's nothing that said that you have to use the loss function. What you can do is you can use any function, g of theta, that you might want. This is still unbiased for the population loss. So the standard PPI estimate will just say, oh, well, I'm going to take the loss. We've seen another estimate, which is no, I'm going to take a multiplier of the loss so that I'm optimally for the variance term. But in general, there's a whole field that is emerging, which is that there's a way in which you should try to minimize the asymptotic variance, and you should, this goes back to theories about semi-parametric efficiency, where, well, if you could, what you would do is you would like to take this debiasing term. This is a notion that comes back again, I think in causal inference, these are control variables, I think they're called. And this is how you're going to modify the empirical loss to achieve minimum variance. So I'm not going to dwell too much on this. I'm just going to say that this is a field that is actively being pursued, which is that, yeah, okay, we got it. So we're going to take the empirical loss and then we're going to modify it so that this thing is still unbiased. But by what do we modify it? And we've seen examples, and then people are now actively researching what is it that we should put to get. So for example, if we were in a GLM model, then if the ratio between the labeled data and the unlabeled data is R, then you have an optimal function for what you're doing, and you could try to learn this function, and that's how you're going to debias your imputed estimate. All right, and so so this is a very current. I think this paper was put on the archive a few weeks ago, and I mean, I guess the point of the point in this paper is that, you know, if you apply this kind of optimal, so this is a problem in which the model was trained on a population that experienced a distribution shift. And so if I use PPI, then PPI is really bad because it's trained on a model that is not what the data I'm seeing is. And so we see that the model is not accurate, and so you have an explosion in variance. But if you're using actually this correctly specified debiasing term, then the interval width will stay constant. And so that's what these authors recommend that you use in practice. Okay, so now I'm going to take these ideas and bring them into a different direction, which is something that is extremely researched at the moment, which is the concept of active statistical inference. So it's just going to take this to the next step. And so this is work with Tiana. And so they imagine that we don't have any labels. And so what now we want to do is I still want to get a confidence interval about a parameter of interest. That's what I want to do, but I don't have any label data. And so it might be, but maybe I have a prediction algorithm that predicts a label. And what I would like to do, I think, is like I would like to combine human labeling or true labeling with AI labeling. So I want to collect at most n of the capital N possible labels Y. And I want to use AI or machine learning to guide the data collection. I want to do two things now with AI. Not only get an estimate with lower variance by using the prediction of the AI system, but also want AI to tell me what should I collect and why should I perhaps not collect and outsource to an AI system. All right, so imagine that we knew for which xi the model, suppose xi is whom I'm going to vote for in the next election. Yi, sorry. So imagine we knew for which xi the model makes a mistake. So for which f of xi is not equal to yi. Then if we collected those guys, we would have a perfect data set. We would, when the model is right, use it. When it's not right, go out and collect the data. Well, of course, that's wishful thinking. But you see where we're going, now because people are doing the thing, I have to go back here. I'm sorry about that. And now we're going to do something extremely simple. Is the key principle we're going to apply is we're going to ask a model for which xi is not certain and collect those y's and predict the rest using data. So for example, if yi is binary, then if f of xi is a probability that the model assigns to y equals 1 versus y equals 0, it comes to reason that perhaps I should, if f of xi is 0.5, it's a hard case. It doesn't know whether it's going to vote for candidate A or candidate B. But if f of xi is 0 or 1, the model is certain. So maybe we should actually collect data in this case, but not in this case, and just impute the prediction from the model in this case. Of course, this can be completely wrong, but as we'll see, the inference will always be correct. If the model is completely wrong, it's just not going to be very efficient, that's all. Okay, so let's look at this. So we're going to design a sampling rule pi, and so we're going to collect a label according to a draw from a Bernoulli with probability pi of xi. If f is certain about x, pi x uncertain about x, pi of x should be close to 1. If f is certain about x, then pi of x should be 0. So this is the example we've seen before. And so we're going to rescale pi so that on average, you're going to get little n samples. So you have money to go out and interview 1,000 people, and we're going to adaptively choose, depending on whether the model knows their y or not, which of these 1,000 people we're going to go and ask their label. Okay, so we're going to have the batch setting where we have a model f and a rule pi, which is pre-trained and fixed. This is practical, but it does not leverage information that we go and acquire through the data collection process. So there's, of course, a sequential model where as we get data, we refine pi, we refine the prediction model, and so on. Right, so that's pretty straightforward. So this is, of course, we prefer this setting because it's more complex and more powerful. Okay, and so now we're going to have in the batch case, very simple, and that's where the relationship with AIPW becomes completely obvious, is that in the batch case, so xi I is 1 if I labeled you, and xi I is 0 otherwise. And now I'm just going to minimize a loss. And the loss is what we've seen before, except that this term, which is a debiasing term, has been multiplied with psi I over pi of xi. Okay, so when pi samples uniformly, and basically we recover what we've seen before, this is the PPI estimator I showed you before, but when pi I does not, it's kind of an important sampling version of PPI. And what's kind of nice about this is that it's unbiased for the true loss and blah, blah, blah. So actually minimizing it with what we want. Okay, so you can see that conceptually it's very simple. The only twist that we do is that we have this term that reflects the sampling strategy. Okay, we're still using all of our AI imputations. This is still a PPI style estimate, but now the data collection is informed by the model itself. And therefore, the debiasing term has changed because the xi's are not sampled uniformly at random. Okay. All right, so still the same problem. Okay. All right. And so you still have the same good old results. In the batch case, you have an average of IID terms, so you're going to have asymptotic normality. Everything is going to be cool. So not much work to do there. In the non-batch term, where you actually update your model after each sequentially, then everything becomes dependent. The theory becomes hairy, and so you cannot just. Then you have to work quite a bit to get what you want, but in the end, you get what you want. And maybe I'll skip the details, but in the sequential case, it's not, because now, of course, now F is informed by what you've seen before. So in the sequential case, you have to prove asymptotic normality, and it's not a matter of slapping on a martingale CLT. It's a bit more involved than that. Okay, but the theory goes through. And now how do you choose pi? Well, you're going to choose pi to, again, now we have the form of an estimate. It's this, whether we're sequential or not sequential. And then, of course, we're going to choose pi to minimize the variance of this estimate. That's kind of the goal. And okay, so we're going to do a little bit of variance calculation, and you're not going to be too surprised that if we're in the regression case where y is a continuous label, and then what does it mean to sample according to uncertainty? Like the more uncertain the model is, the larger the chance of you being a sample. Well, here you can show mathematically that the optimal sampling strategy is basically calculating the expected mean squared error of y given the prediction of your model given x, and that is strictly proportional to the sample. Okay, and they are like, for M estimation, you have similar formula, so we know exactly if we could estimate the variance or the mean squared error at x of your prediction rule, then we know how to sample, and we know how to do the same thing for M estimation. So I think it's fairly intuitive, and that you could do something like this. Okay, and I'm going not in the right direction. And of course, in practice, when you see an estimator like this, I think people who work in causal inference know about this. It's a bit dangerous to divide by pi of xi, especially when pi of xi is very small. So in practice, you're going to do a bit of fine tuning. And so in practice, what you're going to do is you're going to say, all right, look, Emmanuel, your ideas are not too bad, but I'm not sure I really believe you, because if you're a bit incorrect in this formula, see, the good thing is like, this is going to be something like your y minus f of xi here, right? This is y minus f of x. So if I've estimated the variance of y minus f of x very well, then this is no problem. This term is under control. But if it's not estimated well, this variance might blow up. And so I don't want that. And so what you're going to do in practice is you're going to trade off and try to find something which interpolates between, well, let's trust Emmanuel versus let's do the classical thing of sampling uniformly at random, and let's find a good lambda. In general, we're submitting papers to NeurIPS at the moment that's not good enough. In fact, there's many ways of moving smoothly from the active to the uniform distribution. For example, why should it be a linear path? Why not a geometric mean? And so there are paths that are better than others. So you could move from one distribution to the other and try to find along these paths where it's good to land. There's also robust optimization that we built into this to make things really absolutely kosher, but I don't have time to talk about this. Okay. So
$5,000. I watched forward a lot of money with this.
Okay, so here is just to show you again that you can do a lot of stuff with this. So XI here in these examples are news headlines. So these are actually, it's unstructured data, it's text. And YI is an expert human annotation of an article stance on global warming. So it's like what an expert thinks. Is this believes in global warming, neutral, or kind of skeptical of global warming? This is what a human would actually, how a human would annotate an article. And we want to understand, so if this is an example where we have thousands and thousands of articles, and we like to understand what is the stance on global warming in the media at the moment. And of course, we don't have the manpower to annotate all these news things. Okay, and so there's a parameter that we care about. And then we're going to just ask ChatGPT, what do you think is the stance of this article on global? There are three possibilities. Which one is it? All right. And so that's our machine imputation model. And then you see these plots on effective sample size. So if I just use ChatGPT, I'm completely off. And if I use the orange is the adaptive sampling strategy. So they are actually, I'm going to combine human annotations and ChatGPT annotations. I'm going to be very careful about which news headline should a human annotate. All right, that's the orange thing. And so we saw the classical method. I don't need to talk. This is a PPI, so it's very strategic about reducing variance by using the imputation from ChatGPT, but it's not smart about whom should we ask. And then you add an extra layer about this data collection. So you use both the prediction of ChatGPT to both reduce variance, but also query data. And of course, this boosts the sample size even further up. So we actually published a paper that actually looks at a lot of social science about trying to understand how we feel about certain topics. And each time we see plots like this, which is the active inference, has benefits a lot. Okay, so this is public opinion research, same thing. What you can see here is the budget, the number of samples that you save over the classical procedure. And so you see that this is public opinion research. So this is approval of Biden versus Trump. And so you see that here, in the case of Biden, you save a sampling budget of about 90%. So we get 10x effective sample size. And of course, it's because it's very easy from covariates to see for whom you're going to vote. And then this is a budget save of using the strategy over PPI alone. And now in the last few minutes, if I have 5 minutes, I want to kind of tell you about new directions. And one new direction is, again, with Tiana, when I say that Tiana is the pillar of this field, but I really do mean it. She's involved in pretty much everything we do. Here we are actually doing a new thing. This is something we're submitting today to NEURIC, so I'll just show you a little preview of that. Okay, I have, let's forget about inference now. So I have a bunch of X's. I don't have any Y's. So I have an IID unlabeled data points, no labels. So as I'm sure you know, labeling is very expensive. You know, you need humans to read stuff. It's very expensive. I don't have any labels. And I would like to actually manufacture a data set. And in this data set, the labels can be either labeled by an expert or by an AI system, let's say ChatGPT. So my goal is to actually use humans and machines to actually label the entire data set, but in such a way that a certain quality metric is satisfied. And that quality metric is that I would like to use the human as little as possible, maintaining the fact that a certain loss and certain error metric between the correct labels and the labels you give me is less than epsilon with 41 minus alpha. Does this make sense? So I want to be able to say, hey, Google, here is a data set that has all the correct labels, except maybe 2%. And I'm 95% sure that this is actually happening. Okay, and I can perhaps, because maybe a lot of downstream analysis don't depend on the third digit of blah, blah, blah. And so the question is, how do we get probably approximately correct pack labels? So this we're going to call them pack labels. They look like true labels, but you allow for little error. So this could be, if this were 0, 1, it could be the number of times, the fraction that they are not the same. Okay. All right, so here's a method for pack labeling, and I'm going to say it's quite simple. So I make predictions, f of xi, so maybe it's ChatGPT, it's telling me something about the world. And I may have even asked ChatGPT to actually tell me, look, and that's what we do in the paper, how certain are you of the quality of the label you just gave me? How about you give me a range? And so if you give me a range, if I ask ChatGPT to give me a range, I could say, I could look at the width of the range, that's a measure of uncertainty that I could extract from the language model itself. And so I have uncertainty scores that I'm going to call U. U is, if U is high, the model is really not certain about the label. If U is low, it's kind of certain. But you'll see that the theory we have does not depend on this being actually correct or not. It's just like what everything you've seen. We will always be able to give you this. The thing is, if the scoring mechanism is not good, we're going to just ask too many units. All right, so how are we going to do that? So we're going to manufacture a data set. And what the strategy is that we could actually ask a human if the uncertainty score is above U, because the model is very uncertain. Otherwise, use a prediction from the model. That's kind of the scoring. Well, and the question all it boils to is, how should you choose U so that this thing is true? All right. All right. So this is what you're seeing here is essentially the loss as a function of U. If U is small, then humans pretty much label everything, and so the loss is very small. If U is large, then the loss is high because you basically completely outsource it to ChatGPT. Okay, so that's kind of what the loss function looks like. And so we could ask, should I choose U to be this thing? And so if you were choose U to be this thing, you would have a loss function, which is this. Of course, you don't know the loss function because you can't calculate it. You cannot compute it because you don't have the true label, so you cannot compute it. But if you could, you would observe that, well, this is a loss, it's too high, I need to ask for more stuff. Okay, so, I could also ask, this is U, and now we ask a human to do a lot of work, and now the loss is very small. All right, and so in a nutshell, there's an optimal U that would give me a loss of epsilon. Of course, I don't know what that is because I cannot compute this loss function. So what we're going to do is we're going to actually try to build an upper bound on the loss function, 1 minus alpha upper bound. Now, what's extremely important is that this upper bound does not have to be simultaneous. It has to be only, it doesn't mean that this loss has to be for all, no, for each value of U, I need an upper bound. It doesn't have to be simultaneous. That's the key point. It doesn't have to be similar. I'm going to construct an upper bound. And then I'm going to look at when is my upper bound crosses epsilon, which is a target that I have. This is my U hat. I label everything by humans above U hat and not below. Below, I'm going to outsource it to ChatGPT. The theorem is that these are pack labels. That it actually does exactly what you see. It's very simple. And for those of you who are worried about what I'm saying, imagine you're looking at all U simultaneously, blah, 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 multiplicity correction. No, there is no multiplicity correction here because of monotonicity, essentially. So there's no multiplicity correction of any kind. And so this you're going to see is this. So, this is a lot of misinformation, stance on global media bias. That we know have been annotated by humans, and then we are going to play this game of using pack labels. And the error is, we want an error of 5% with probably 5% or less with probably 95%. And so I use pack labeling, and the error is exactly what you want. This is where you see that the method is not conservative at all. the area is 5, that's the target, 5.17, 4.95. And since this is the amount of label that has been labeled by an expert, it's not a U because the model is not super good at actually finding out what we should label and what not. If I use AI only, of course, that's not good. If I just decide to label all the UIs, then I'm just doing too much work. That's not what I want. If I use all the UIs, which are 0.1, sometimes I'm conservative, sometimes I'm not. So it's not good either. And so you really need a method like this to actually label. And so at the end of the day, you know what you're holding. Okay. So we have many more examples in the NeurIPS paper we're writing at the moment. Another thing, but I think my time is up, is we are trying also to extend this to so this is work with Genima, a Stanford student, sometimes so this is active inference. We've seen this before, but sometimes we cannot assume that the thing is the solution to an M estimator. So I'm going in the wrong way. I'm sorry. Anyway, maybe I'll skip this part. Like, for example, right now we're estimating log ratios. So, for example, I might be interested in odds ratio. Like maybe you have two types of molecules, and I want to know what is the expected value of Y. The probability that Y equals 1, given that X in a certain group, divided by what is Y equals 0 in another group over. Now I want to see how it varies across groups. So this is an odds ratio. This is not so this is a parameter of this kind. This is not the solution to an MSD problem. I want to know stuff like that. And so what we're doing is we're adapting a lot of the methods you've seen to actually design a sampling plan, which is that if this is your goal, how should you design pi of xi so you have low variance and extremely robust at the same time? That the estimate doesn't go crazy. And okay, and so we do this by essentially adapting ideas from control, where we're going to set up optimization problems that are well behaved and quickly solvable to actually design a sampling plan that obeys constraints that we do care about. Okay, so I think my time is up. I think this shows that it works well, but I don't want to take too much of your time. So the title of this talk was Statistical Reasoning in the Age of AI. So here I'm saying, how can I use Gen AI to impute data and yet get reliable scientific conclusions? I think in the launch seminar, I discussed a lot of the possible interactions between statisticians and AI. We talked about data attribution, on what data should I actually train a model? How do I calibrate the output of an LLM? How do I generate, if I have a prediction from an AI, but I need a sort of a selective error rate to be controlled, how do I do this? So this is for a different talk. Today, I just showed you or explained how we can use data generated by AI and yet still design. Thank you very much.
Any questions? We'll take some questions.
You want to ask a question? Oh, go ahead.
No.
Okay, no, please go ahead. I see.
So, first off, thank you. The first part when you say cross PPI in causal inference missing data, we've got it cross PP.
Okay.
All
right,
and it's all over the place.
It's all over the place.
Yeah, it's all over the place.
Okay, thank you.
And then the second thing is, I'm Andrea Magnitsky. I worked on semi-parametric theory for missing data.
Okay.
In the 90s with Jamie, we derived a general theory for you give me any semi-parametric model, you give me any parameter, any functional that you care about, and I tell you how to construct all the influence functions
I see.
in the missing data. I mean, you tell me what parts are missing, they have to be missing at random, and I tell you how to construct all the influence functions and the efficient influence functions. And you could use that to calculate here, efficient estimators. Like when you say, well, we have MST, which is some parameters of M estimators, solving M equations. It doesn't need to be like that. It can be any parameter. Because the theory is there. We know how to do it. So we can.
So I need to take a look here.
Okay.
Thank you.
I wanted to ask a simple question. So in the pack results that you showed, so what determines the width of that confidence interval for the loss function? So you give me upper bound,
Right.
what are the factors that will determine how far that upper bound is from the function?
So what you can do is like this loss function, I suppose I give you a random sample of the AI annotation and the true annotation, right? Perhaps even condition on some features of X, right? It's an IID sum. And so it's very easy for me to construct an upper bound on the sum of IID 10. Right? So if I were to look at my table and sample things uniformly at random, and then starting to compare the true label with it, I would get a sense of, for any value of U, how big this is. It doesn't have to be even the good thing about the theory, because there's an enormous, the fact that the thing, this loss function is monitoring you is extremely important. So I'm going to do it point by point. I can get, like, even like say, suppose I could do the central limit, I could do more fancy stuff. I can use martingale to actually get upper bound a bit like what Wobbe, Smith, and Ramdas developed. But I don't have to do this. Let's say I use the central limit theorem, I get an upper bound. And I get an upper bound even, I can get a similar upper bound like, oh, well, there's an Austerlitz course, so this is not sampled uniformly at random. That's okay. It's still a random sum.
And so even without having actually Y in practice, because
No, I need an upper bound, right? So, but I have sampled, maybe biased towards high values of U, right? But I have an upper bound because this is not a complicated object. This is, in the case of the Y's being sampled uniformly at random here, we know how to do this, right? So we get this. Basically, these are, like, if we call them ZIs, like fixed U, call them ZIs, they are random draws from this table. Of course, I have upper bound.
A clarification question on that, because maybe you have the same confusion. So I thought at the beginning, you don't have any of the Ys, right? And now you're gonna, is it an adaptive?
Okay, so you get, there goes again a batch mode and a sequential mode, and, we can do this in batch and sequentially. But what we could do is we could sample like 30, which is a very low budget, uniformly at random, so I can give it over long run, get more, we find the upper bound.
So fair did that to figure
Right,
out.
and so that of course we can do this. Of course.
So do we what can you assume about the use and what can't we?
Nothing. The U's are whatever. For us, it's like literally, in the paper we're submitting is like, we asking ChatGPT, how do they feel about that this is a left-leaning article? Are you sure that it's left-leaning? If you give us a probability that it's a left, that's what we use.
If we make some, because I've seen nothing. Sorry.
But your question is good. This can be arbitrary, but the saving of human labeling will depend on their quality. If they're good quality, if indeed, if there is bad quality, if it's actually the other way around, I might actually, to certify that I have an epsilon upper bound on the loss, I may have to see N, right? And so, or at least 1 minus epsilon, right? So the U is helpful. It's like what I like about this stuff and everything we've seen today is that my machine learning model, I have no assumption. I want to treat it as a black box. I'm not saying it's anything you like. And what we'll do is, first of all, we'll never lose because of this power tuning where we can up, we're going to revert to classical stuff if we need to. And so the quality of the use, the quality of the pi, the quality of your error estimate, the quality of your prediction doesn't matter. This is going to say that, yes, you're not very efficient. Like, yes, you saved me time, but only 5%. Whereas if you had very good uncertainty estimate, I might save you 90%. So in the New York paper where we deal with images, where we ask now a vision model to actually tell it's a cat, it's a dog, then it's very good. It's very, very good. And now, there's a lot of stuff you just can outsource to the AI system. So no matter what U is, the properties of inference, which is in this case, this one, it's always true. The matter is just, do you have power? Did I save you time? And that depends on getting good use.
Maybe the use would be better instead of asking, like, what do you think is an uncertainty, like refresh and ask a bunch of times.
Yeah, we do that too. Yeah. So we do that too. We ask the same thing several times. In fact, you can even ask several LLMs. You ask Claude, you ask Gemini, you ask ChatGPT or one. And if they give you all the same answer, you're pretty certain. If they give you different answers, you can ask them several times. And that's a very good score of uncertainty. Absolutely. We can have a tournament. In fact, there's an extension of this model where what we're doing is we say, you have the cost of asking a human, you have the cost of asking Gemini, and then Llama and all these things, and they are like different costs. And how do you optimize for cost now? Because the cost of querying an LLM is not zero, but it has a cost. And so now I have all these LLMs sitting out there. They can all issue prediction, but they have a cost. And how do you allocate? Like this guy, I'm asking human, if not, which LLM? And this guy, if not, and so there's an extension of this thing to minimize cost when you cannot ignore the cost. And you have several models that can actually give you an answer.
So in your power tuning procedure, there's a lambda parameter,
Right.
like an index, to define the procedure. So do you,
So it can take many different forms than this. Like, for example, another one might be
yeah, and I guess I was referring, you had an earlier version of that lambda, right, where you have the naive, sort of inefficient estimator and more
Right.
efficient one. And so how exactly do you select lambda data adaptively, and if so, does that have implications for you?
yes, it should. I mean, in practice, we don't worry too much. But yeah, so what you do is you choose lambda by cross-validation typically. And then can you prove a theorem for the cross-validated lambda? And suppose you do, have I done it? No. But in practice, you choose lambda on something. That's a mixing between.
One last question. The question for the. Yeah, so now, for the little data, would it be possible to use this great like if you get a model to find things, can you able to find things in that the first one time, or not matter?
Can you please repeat the question?
Then you come to the label you know what is for finding the other disciplines, like if you had knowledge.
Can I use a label that I have not collected?
That you have now collected, so like find things like that.
Yeah.
Okay, that's.
So you're asking whether there's a sequential version of this. I think so. Whether we worked it out, not completely sure, but yeah, I think the only thing we need is do we have, okay, so maybe we skip this. It's a bit long, I'm sorry. Do we have at any given time an upper bound on this? It's the only thing we require. If we have a valid upper bound, not simultaneous, at a fixed u, then we're in business. So in the sequential mode, the question becomes, can we get this? And I think we can, but I can't say that I've answered this question.
Okay, let's thank Dr. Emmanuel Candes. Have some mind refreshment on the back, so please help yourself, and thanks everyone